Okay, so for part 1 of homework 1-2 here, let's just jump right in. So question 1, if the acceleration of an object is negative, the object must be slowing down. That one, hopefully we all are pretty comfortable with saying is false, right? Just because it has a negative acceleration does not mean it's slowing down. If the object was also moving with a negative velocity in the negative direction, then if it had a negative acceleration, it would be gaining speed, right? The number would be getting bigger in the negative direction. So maybe originally it was 10 meters per second, has an acceleration of negative 5 meters per second squared. So after a second it would be moving at negative 15 meters per second, which means its speed, which is just a numerical value, right? The 10 is obviously smaller than 15, right? 15 is increasing its speed. Anyway, make sure you're comfortable with this one. This is one that hopefully we're good on from last year. 2. Suppose that an object is moving with constant non-zero acceleration. Which of the following is an accurate statement concerning its motion? In equal times, its speed changes by equal amounts. That's kind of a tricky one, right? We'll leave that one to come back to. Equal times, its velocity changes by equal amounts. Well, what's the definition of acceleration, right? Acceleration, if it's a constant acceleration, is change in velocity over change in time. And so in equal periods of time, if the acceleration is constant and not zero, if the acceleration is a constant number, then for every second of time, the velocity has to change by an equal amount. So this is actually true. This is our best answer for this one, which you could then make the argument with the speed as well, but we'll look maybe a little bit more into that in just a moment. But in any case, let's go through the others and just make sure we're comfortable ruling this out. In equal times, it moves equal distances. That's not necessarily true, because velocity, we know, is distance over time, right? Or displacement over time. But the velocity is changing, so with every second, the distance over 1 second would be changing as well. So that's definitely not true. A graph of its position as a function of time has a constant slope. So again, if my x versus time graph had a constant slope, so let's suppose that this was just a line, well, the slope of this graph would be the velocity. And so if this had a constant slope, the velocity would be constant, which would not be a non-zero acceleration, because if it's a constant velocity, that tells us it's a zero acceleration. There is no acceleration. So that's definitely not true. And then a graph of its velocity as a function of time is a horizontal line. Well, that's really the same as d, right? If if d is representing a position that has a constant slope, any velocity graph coming from this graph would be a horizontal line. And again, the slope of a velocity versus time graph would be the acceleration, and obviously any horizontal line has a slope of 0, and therefore the acceleration would be 0, not non-zero. Okay, so the trickiest one here to rule out is A, but because acceleration is defined through velocity, B is definitely our best answer. So question 3, the motion of particles described in the velocity versus time graph, we can say that its speed does what? So this is a good example for illustrating again the difference between velocity and speed, right? We know that the velocity is changing at a constant rate because the slope is constant, right? So the acceleration would be constant, which means again, if the acceleration is constant, then my change in v, my change in velocity over my change in time, is constant as well. But that doesn't necessarily mean that the speed is constantly increasing or constantly decreasing. If we look at the speed, we just want to worry about the absolute value of these numerical values here. So what I mean by that is this starts at maybe about negative 2.5, but in terms of speed, it's moving at about 2.5 meters per second. Well, for the first couple seconds, that speed is actually decreasing, right, because we're approaching 0. So after the first second, it's maybe 1.6. After 2 seconds, it's just about 1. And after 3.5 seconds or so, that speed is at 0 meters per second. So the speed initially decreases, but then as we pass the x-axis, right, the speed begins to increase. The value begins to go from 0 up to a higher magnitude. So option D is the best one here. It decreases speed and then it increases. So this goes back to what we learned way early last year. As the graph approaches the x-axis, the speed decreases if we're looking at a velocity versus time graph. And it is important, it's velocity versus time. Okay. Anyway, good question to go back and revisit if you haven't seen it for a while. Question 4 here hopefully is a pretty basic one. They give us a velocity versus time graph, and they ask us what is the direction of the acceleration at t equals 0.5 seconds. So here at about 0.5 seconds, so somewhere right about here, I'm curious what is the direction of the acceleration. Well, because it's a velocity versus time graph, the slope would be change in velocity over change in time, which just so happens to be my acceleration. So all I really have to do is figure out what's the direction of the slope at that location. Well, if I draw the tangent line, it's supposed to be a tangent line, if I draw a line that touches that at exactly one point, it's very clear to see that that has a negative slope, right? It goes down as I go from left to right, so that tells me it's in the negative x direction. Okay, so hopefully this was a pretty easy question for us to get through. Question 5, on the other hand, maybe takes a little bit more thinking. Definitely a different way to work through this. Okay, so for those of you that are curious, if you want to just check your answer, the correct answer is A. So if you feel confident in that, again, feel free to kind of jump ahead. But obviously, I think most of us will want to look at this question. It is a tough one. The way that I work this one, and the way that I think sometimes makes it helpful. So we know the markers are equally spaced. Right? They tell us equal distances along the starting. The car reaches its final velocity, final speed of 140 kilometers per hour. We're curious, where does it reach 70 kilometers? Well, the way that I would recommend working this is I'm just going to define this total distance. I'm going to define this total distance as, let's just say 100 kilometers. Since our units are kilometers per hour, I'm just going to keep it consistent. Okay, the reason I'm going to do that is it tells me that it has a uniform acceleration. And so by defining the total distance, if I look at the total, let's think about what measurements I know. Well, I know the initial velocity because it started from rest. So the initial velocity is 0 kilometers per hour. I know its final velocity after that total distance, which I'm just calling 100 to make it easy for me. All right, so the final velocity is 140 kilometers per hour. And then I know that I'm just defining that total distance as whatever number I want. So you could define this as x, you could define this as a specific number, 1,000, whatever makes it easy. But the reason that I'm doing that is it will give me a chance to numerically solve for the acceleration. Right? So since I know these three measurements, if I jump in with the final velocity squared equals my initial velocity squared plus 2a delta x, I know 3 of those 4 measurements and therefore can find the acceleration. Okay, so I know the final velocity is 140 squared, I know the initial velocity is 0, plus 2 times, I don't know the acceleration, but I'm just defining the total distance here as 100. Okay, so then when I solve this, I get the acceleration to be, based on my number, based on this, 98 kilometers per hour squared. The reason that's helpful is now I can reset and start from 0 again and say, let's figure out how far we're going to go when we reach 70 kilometers per hour. Okay, so I'm going to reset and I'm going to say, how far do I have to go? Do I have to go 50? Do I have to go past 50 or less than 50 in order to reach 70 kilometers per hour? So I know the acceleration is still 98 kilometers per hour, or per hour squared, excuse me, because they told me it was constant. I know the initial velocity is still 0 because I'm going right back to the starting point. I know the final velocity that I'm curious about is 70. So once again, I have 3 of my 4 measurements. If I jump right back to this same equation, I'm just going to solve for delta x instead of a. So I'm going to do 70 squared equals 0 squared plus 2 times whatever the acceleration I found. Again, if you used a different number, just whichever acceleration you're using, and then times delta x. The key here is when I solve this, based on my numbers, I'm actually going to get delta x equals 25. No matter what numbers you used, you should have figured out that delta x is only about a quarter, right, of the total distance that you worked with. Okay, so delta x equals 25. That tells me that this car is going to reach 70 kilometers per hour somewhere before marker 1. So again, a couple different approaches you could take to this one. I think maybe the easiest one though is just to make a total distance, find the acceleration, and then use that acceleration to find the distance it travels to reach 70 kilometers per hour. Very good question. This is definitely the type of question I could see them throwing at us on maybe an AP exam, or obviously then on either a quiz or a test. Cough, cough, hint, hint, wink, wink. Know how to do this one. Anyway, if you do have further questions on this, come find me and let me know. Okay, so question 6 is similar to one of the questions we had in the first homework assignment. I'm going to do like I did in that first homework. I'm going to go ahead and start by writing down the correct answers. So the acceleration, the instantaneous acceleration for part A would have been about 12.82 meters per second squared, and then the average acceleration would have been 4.21 meters per second squared. Okay, so again, if you feel confident in those answers, feel free to jump ahead, or this question will probably end this first part, so you can just start the second part of the video. But in any case, for those of us that weren't confident with this or just want to see it again just to review, let's go through it. So they give us the position function, they give us all the values to plug in, and they tell us we're in meters per second. What is the instantaneous acceleration? What is the average acceleration? Okay, so I'm going to start by just plugging in, filling in my measurements, right? So I've got 4.1 t to the third power minus 2.2 t squared plus 1.7 t. Okay, that's a 7, not a 2, by the way. So that's the position function. I'm curious about the acceleration and the average acceleration. So in order to find the instantaneous acceleration, I need the acceleration as a function. So I need to get there by differentiating a couple times. So I'm going to find the first derivative, which will be my velocity function. So after doing the first derivative, I use the power rule, and I just bring these numbers out front, right? So I end up getting 12.3 t to the second minus 4.4 t to the first plus 1.7 times 1, so still just 1.7, and that t has gone away. So I've now got my velocity function. To find the instantaneous acceleration, I want the acceleration function, so I'm going to do this one more time. So I'm going to find the second derivative of my position. Okay, so this was my first derivative, was the velocity function. The second derivative, the derivative of that is my acceleration function. So again, using the power rule, 24.6 t to the first minus 4.4, the t is gone, and then the 1.7, because we can think of this as t to the 0th power, and then bringing that 0 out front, the 1.7 is gone as well. So now that I have my acceleration function in terms of t, if they want me to find the instantaneous acceleration at any given time, I simply take that time and I plug it in. So in this case, I'm going to take the acceleration of 0.7 seconds, and I'm going to plug it into my equation. So 24.6 times 0.7 minus 4.4. And when I do that, that's where I got the first answer of 12.82. Okay, so 12.82 meters per second squared represents my instantaneous acceleration, so the acceleration at that exact instant in time. So then, like the question we saw in homework 1, the key here is, how do I find the average acceleration? Well, let's go back to the definition, right? The definition for average or constant acceleration is change in velocity over change in time. So if I want to find the average acceleration, I'm actually not going to use the instantaneous acceleration or the acceleration function. Instead, I'm going to use the velocity function, and I'm going to find my velocity at 0.7 seconds minus my velocity at 0 seconds divided by 0.7 seconds, since that is my change in time. So I'm going to use my velocity function and find the velocity at 0.7 seconds. So again, just plugging that value in, and since I'm running a little short on time and space, I'm going to assume that we can just plug that in. So when you plug in your 0.7 seconds, I get that to be about 4.647, depending on where you round it. Obviously, you could round that off at 4.65. When I plug in 0, because all of the velocities except the 1.7 depended on 0, I know that my velocity at 0 seconds is just going to be 1.7. Right? That guy wasn't actually there, it was just there to express it. So both of these would become 0, so I get 1.7 seconds, or excuse me, meters per second. So then my average acceleration again is simply taking the 4.647, my final velocity, minus my initial velocity, and the order here is very important that we do final minus initial, since we're talking acceleration, and acceleration is a vector. But in any case, when I calculate that, when I solve that the rest of the way out, that's where I get my 4.21 meters per second squared. And it is a positive, indicating that it is a positive acceleration during that period of time. Okay, so the average acceleration is positive, and the instantaneous acceleration is positive as well.